me very briefly introduce today's speaker, Berthold Jäck. And so for those of you who are not familiar with him, so he got his PhD nominally at the EPFL, but working at the Max Planck Institute for Solid State Research in Stuttgart in the group of Klaus Kern. And the title of his thesis was Josephson tunneling at the atomic scale, the Josephson effect as a local probe. After that, he moved on to Princeton as a postdoc in the group of Ali Yazdani from 2016 and 2020. And then since 2021, he's an assistant professor at the Department of Physics at the Hong Kong University of Science and Technology. And his group called Laboratory for Quantum Matter and Microscopy, they focus on microscopic investigation of correlated and topological electronic phases in low-dimensional materials, and combining low-temperature scanning tunneling microscopy and also device fabrication and fabrication of quantum design of quantum materials. And they are also in the business of developing novel quantum microscopes for spatial and temporal resolved study of electronic quantum phases of matter. And today, the title of Berthold's talk is From Very Curvature Multipoles to Non-Trivially Localized Electrons. And I think with that, we very much look forward to your talk, and please, so glad that you accepted our invitation. And please, the floor is yours.
Thank you, Peter, for this very nice introduction, and especially Peter and also Jose for inviting me over to give this virtual talk. Yeah, as the title says, we are interested in a broad range of properties of Kagome metals, and to this end, we combine various measurement methods. Today, I will talk about the recent results we obtained by studying a specific family of Kagome metals. Yeah, so this work would have not been possible without these fantastic people here. I think I mentioned all the names, so let's just save the time and move on to the question of why Kagome lattice materials are so interesting. Essentially, they're properties derived from the relatively unique lattice structure that is composed out of corner-sharing triangles here. And there are essentially two features of this lattice that result in rather unique electronic structure. First of all, you have this sort of six-fold rotational symmetry and more than one atom per unit cell. And this essentially gives you a Dirac cone at the K point of the band structure. And now, obviously, and we know this for many years, the Dirac cone can be a source of very strong barrier curvature, essentially resulting in topological electronic states and even can insulate and quantum anomalous Hall states if you find the right material. Moreover, what makes this system also interesting is that the eigenstates residing on adjacent lattice sites of this honeycomb Kagome lattice center have an opposite phase. While there can be a finite hopping term allowing the electrons to essentially hop out of this or away from the central hexagon, this opposite phase essentially cancels out this this hopping pathway, leading to localized electronic states. Now, when we look at this in a momentum space picture, obviously such a localized state then corresponds to a electronic flatband. Now, we are by now, I guess, very familiar with electronic flatbands, most notably due to the various types that have been found in moire materials, but also here on Kagome lattices, a vast, I guess, literature body exists that predicts various states, such as zero field, fractional, quantum Hall states, and so on. Now, because of these very interesting electronic structure features, for the past years, various Kagome metal families have moved into the spotlight. I guess most notably, perhaps the iron tin platform, which has been around now, I don't know, maybe 4 years. And then more lately, the cesium, but also rare earth-based vanadium, antimony, and tin platforms. Today, I will focus on what we have done in the past 2 years on the iron tin family. Now, as Peter already said, I have a background in scanning tunneling microscopy and quantum materials exploration. And now the approach that I take here in my own group is the following. What always bothered me, say, as a scanning tunneling microscopy experimentalist, when I was working, for example, with Ali in Princeton, is that essentially when you obtain results at the atomic scale, you ask yourself, how does it connect to what other people find at the macroscopic scale, say in electrical transport measurements? So for the SDM community, I guess this has changed a little bit over the past years when we were able to study 2D devices like magic angle, twisted bilayer, graphene, when really these two directions started to connect in a way. And this has been, in a way, a sort of inspiring event for me in that I now want to continue with this work, not necessarily on these 2D devices right now, but also doing similar types of experiments using epitaxially grown thin films. And so what we have been doing here in Hong Kong is to set up a relatively unique thin film growth combined SDM system that combines an MBE, which basically can grow any type of film you want, with a low temperature scanning tunneling microscope system. And with the system we have here, we can essentially grow thin films either for SDM measurements, but also for device fabrication that essentially allows us to study both the electrical transport properties of these thin films and also the local electronic and magnetic structure using SDM measurements. Okay, let's jump right in to the topic. And the first part I want to talk about is the topological electronic states and how they can be detected in electrical transport measurements. I guess by now, many of you have seen many examples of anomalous Hall effects. And when you look at it more broadly from a higher perspective, what we're basically doing here is to measure the impact of a finite barrier curvature on the material properties. What specifically happens is that if your electronic system has a finite barrier curvature, this can lead to a finite contribution to the Hall conductivity sigma xy. And what you essentially find here is a momentum space integration of the barrier curvature. Now, when time versus symmetry is broken, this contribution can be finite, and this leads to this very famous anomalous Hall effect, for example, in various ferromagnetic materials. I guess a very specific example that we can detect, for example, in Kagome materials is that if we combine a Dirac cone with spin orbit coupling and ferromagnetism, we can essentially get out this Dirac cone giving rise to a very strong barrier curvature. In the fully quantized limit, when the Fermi level resides in this charge gap here in between, then we can even find a fully quantized Hall response, a quantum anomalous Hall effect. So the idea of using now the anomalous Hall effect to study topological materials obviously has been around for many years and also found entry into the study of Kagome systems. And I think most notable, the first work that really showcased this relation was done by Joe Czekelsky's group back in 2018, when they could show that the Dirac cone of iron 3 tin 2 can give rise to a quite sizable anomalous Hall effect in the electrical transport properties. So far, so good. So more recently, it turns out that you cannot only find barrier curvature multipoles, which say arise from a uniform barrier curvature distribution and the Breuer zone. What also is possible are so-called barrier curvature multipoles. As a matter of fact, almost 10 years ago already, Inti Soderman and Liang Fu predicted that in some materials that have a very low crystalline symmetry, the so-called barrier curvature dipole can exist. Unlike the barrier curvature monopole here, which basically is, has a uniform barrier curvature across the entire Breuer zone, the barrier curvature dipole has a non-uniform barrier curvature distribution. And this can give rise to so-called second-order nonlinear anomalous Hall effect, where when you apply a longitudinal excitation current along such a device, you can pick up a second-order response, a second-order Hall response in the transverse direction. I believe this was measured between contact 3 and 4. So what essentially happens is that you source a longitudinal signal at frequency omega, and the barrier curvature dipole converts this to a transverse output at frequency 2 omega. Now, this has been observed soon later by Chong Ma in Pablo Herrera's group at MIT. And in the meanwhile, our understanding of these multipole effects has been growing. It turns out that while this specific dipole needs a very low crystalline symmetry, I believe here in tungsten telluride, just one mirror plane, antiferromagnets can host a larger variety of multipole effects. In fact, it was predicted by my dear colleague Vic Law here at HKUST that Up to 90 magnetic point groups in antiferromagnets can give rise to various types of nonlinear anomalous Hall effects. In other words, 90 magnetic point groups support different types of barrier curvature multipoles. Today, I will talk about the barrier curvature quadrupole, which is predicted to induce a third-order nonlinear anomalous Hall effect. To demonstrate this phenomenology, we're interested in the Kagome magnets of the iron tin family. What makes these materials so interesting is basically summarized here in this overview on the left side by Mingyu Kang's work. What is quite interesting here about this family is that you can very accurately control the both electronic and magnetic properties of these materials by combining different types of elements like iron, manganese, cobalt, germanium, tin, but also changing the stoichiometry. For example, the 3-1 stoichiometry of iron tin gives rise to these out-of-plane ferromagnet that we just talked about, which features a relatively large anomalous Hall effect. On the other hand, when you look at an 1-1 compound like iron tin or later cobalt tin, you have a different spacing. Instead of having sort of Kagome bilayers spaced by a Stannian layer, you always have one Kagome plane spaced by one Stannian layer from another Kagome plane. And now this has a very important ramification. First of all, as we see later, this 1-1 stoichiometry essentially allows you to have a nice Kagome flatband. More specifically, now in this context of these multipole effects, what it does is it gives you an antiferromagnetic order along the out-of-plane direction. Here, iron tin, for example, is a so-called A-type antiferromagnet. It has a relatively large above room temperature Néel temperature, and essentially stacks ferromagnetically ordered Kagome lattices in plane moments, antiferromagnetically in the out-of-plane direction. Now, when you just look at a native iron tin compound, you'll find it has a MMM1' symmetry, which preserves the combined PT symmetry. So it's not expected to show any anomalous Hall effect. However, what is interesting is that if you slightly reduce the symmetry, the magnetic symmetry of the system, for example, by canting the spins out of plane, you lower the symmetry to 2m, which has a finite barrier curvature and barrier curvature quadrupole. What is interesting is now that this canting of the spins out of plane canting has been observed previously by a group at Oak Ridge National Lab when you put this compound simply in a large enough magnetic field. You can actually analyze the effect of the spin canting by setting up a simple tight binding model calculation of such an A-type Kagome antiferromagnet. What we've been using here is this very well-known tight binding model by the Marcel-Franz group from some 15 years back to essentially evaluate the situation. And what we find is that if we take such a A-type antiferromagnet on the Kagome lattice and include some spin canting, we can essentially find, now here in the top row, a finite barrier curvature, we call it a monopole, and quadrupole moment, as long as the magnetization in the out-of-plane direction, that is the canting, is finite. Interestingly, even if this material goes into the paramagnetic phase, this is shown here at the bottom, you'll still would find a finite barrier curvature monopole and quadrupole contribution. So with this understanding of the basic magnetic and topological properties in our pocket, we went on to synthesize thin film of this compound. What we have been doing here is essentially adopt a growth recipe from the Czechowski group, where we have been growing thin films of iron tin and also protecting them by a capping layer of barium fluoride. When we realize this growth, it turns out we end up with very uniform, nicely ordered films that essentially crystallize in a single phase. They're not necessarily single crystalline, but we don't observe any other phases, such as iron 3 tin 2 or iron tin 2, and so on. At a very fundamental level now, when we just make a simple Hall-bar device and first study the longitudinal conductivity, we find that this material essentially behaves like a fairly good metal with a reasonably high residual resistance ratio, and also see that we can pick up the antiferromagnetic transition at the Néel temperature at about 355 Kelvin. So without going too much into the details of these, say, materials characterizations, what we essentially find here is that both the basic electronic but also magnetic properties here are very consistent with the various works that have been published on this compound over the past years. What we're interested in now is to essentially see if we can pick up these barocurvature quadrupole moments when we expose this film to an out-of-plane magnetic field as predicted by our toy model calculation. To test this prediction, what we have been doing is now etching Hall-bar devices and applying a longitudinal current drive, an AC current drive along the x direction. Then we essentially used log-in techniques to pick off both the longitudinal resistivity as well as the transverse resistivities at the first, second, and third harmonic. Our very first experiment I show you now is conducted at room temperature. So what you can see here now is the result of these measurements summarized on the right side. We observe a small anomalous Hall effect in the first order response. On the other hand, the second order response is completely absent. What is interesting, however, is that we observe a relatively strong third order response, which is exactly what you would expect from our toy model. We would expect a first and third order response, but no second order response owing to the symmetry constraints. What we also find is that the third order response is odd in magnetic field, meaning it's zero at zero magnetic field. And this is important because a third order anomalous Hall effect has been observed before, induced by the barrier connection polarizability tensor. However, this one is even in magnetic field and therefore can be distinguished from our observation. In order to understand this observation, we moved on to characterize the third order anomalous Hall effect. The first thing we did is to check on the symmetry constraint. We know if the spin is not counted out of plane, there should not be a third order anomalous Hall effect. So what we've been doing now is a rotatable sample holder that allows us to rotate the sample from the out of plane to the in plane direction. Shown in blue here is now the result when the field is applied along the out of plane direction of our Hall bar. And this basically reproduces what you've seen on the previous slide. Now, when we rotate the same sample to be parallel to the magnetic field direction, meaning the field is pointing along the in plane direction, we do not observe a third order Hall response, except some noisy background. And this is exactly consistent with our expectation that a field would be needed to essentially break the PT symmetry by slightly counting the spins. Next, what we also did is to study the temperature dependence of this third order anomalous Hall effect. Interestingly, when we started very low temperature, we observe a rather vanishing signal. As we now increase the temperature from, say, 2 Kelvin to above room temperature, we see essentially a monotonous rise of the anomalous Hall amplitude. And just near the Néel transition temperature, suddenly the signal decreases and changes sign. And this is quite an interesting observation. It turns out from other theoretical studies we conducted over the past year that this is not a very universal observation for the third order anomalous Hall effect. It's not basically required by symmetry. However, as a matter of fact, it kind of shows that the observed third order effect is very sensitive to the underlying magnetic symmetries. Meaning, if you have a change of magnetic symmetries, in this case from an anomalous, from an antiferromagnet to a paramagnet, which is counted, still this can change your overall barocurvature in a way that even the third order effect changes sign. Of course, one can argue that first order, second, third order Hall effects, they can often be related, for example, through there could be some diode effects that induces a higher order response. There could even be some, self-induced Joule heating that can lead to a self-induced orbital third order response. To exclude all these other possibilities, we have conducted various types of control experiments. So we find linear IV curves in two-terminal transport, which excludes any rectification effects from, say, a diode. Our Hall amplitudes scale basically cubic with a driving current for the third order response and linear with the drive current for the first order response, which is exactly what you would expect for such a scenario. And also we made sure that the third order response that we pick up is not simply a residue of the first order signal that kind of leaks into your pickup of the third order effect. And so to check that, we tested different types of setups with different roll-off characteristics. So this put together, we're quite confident that what we see is a true third order Hall response. The question that now arises, how can we identify the origin of this third order Hall response? It's seemingly consistent with our toy model, but what can we do here? Well, the best thing we can try to convince you that this is coming from a barrier curvature quadrupole is to set up a so-called scaling theory. The idea behind this scaling theories, which now have been around for maybe 15 years or more, is that there is essentially a scaling relation between the Hall conductivity and the longitudinal conductivity. Generally speaking, the expectation is that the intrinsic contribution to the Hall conductivity arising, for example, from barrier curvature effects should be temperature independent. And with this knowledge in our mind, we can then develop scaling theories to determine this temperature independent contribution to the anomalous Hall effect. In our case, for example, you can already pick this up when you look at the electric field ratios of the anomalous Hall effect versus the longitudinal conductivity. When you plot it, you can basically see that the amplitude of this ratio decreases, but picks up essentially a temperature-independent value as we go to larger temperatures. By contrast, the longitudinal conductivity does not show the saturating behavior towards larger temperatures, which is exactly what you expect for a metal. Now, just this plot already gives us a hint that there is an intrinsic contribution to these Hall effect, which we now analyze in the following. What we've been doing is now to set up a scaling theory for the third order Hall effect. And essentially what you want to do is you want to plot this ratio here of the electric fields and then fit it with a function that essentially connects the skew scattering contribution, which scales with the conductivity to the power of 2 and vertical intercept beta. And now if we fit this ratio of electric fields with this function, we can readily extract the intrinsic contribution coming from the barrier curvature quadrupole moment. And as a matter of fact, this is quite strong. What you find is that at room temperature, about 95% of the anomalous Hall conductivity originates from the barrier curvature quadrupole moment. And what is also interesting is that essentially at lower temperatures, when we go, say, towards 100 Kelvin, we find that this ratio basically is a function of the conductivity. And this is what it should be. Because at lower temperatures, one would expect that skew scattering starts to contribute to your anomalous Hall effect, and it does exactly that. And it also, in our case, shows that the scaling you would expect, which is proportional to the scattering time to the power of 4. Yeah, and because we're not aware of any other effects that show these scaling characteristics, except for the barrier curvature quadrupole effect, we're quite convinced that the barrier curvature, the nonlinear anomalous Hall effect, the third order nonlinear anomalous Hall effect in our case really arises from the barrier curvature quadrupole. And this concludes my first part. So what we have been showing here is that essentially antiferromagnets are a very rich material platform to study barrier curvature multipole effects. As a matter of fact, 90 point groups are predicted to support these multipoles, and the symmetry groups that should support those in leading order are shown here in this table. Now, what we could demonstrate also is that by using Hall measurements, we can essentially find evidence for a barrier curvature quadrupole in spin-canted iron tin at room temperature. And more broadly, what we believe our study now really does, it opens a door to study these multipole effects on various material properties, on the optical, but also thermal properties using nonlinear transport protocols. From a practical viewpoint, what is quite nice, I believe, about this work is that it also shows that the third order Hall effect is very sensitive to the electrical, to the antiferromagnetic phase transition. So we anticipate that under certain circumstances, such a higher order Hall effect could be quite useful to characterize antiferromagnetic phase transitions using transport measurements, which often is quite challenging. Yeah. So beyond what I've shown, of course, we try to expand on our work and currently look for other materials where we hope now to find these higher order non-anomalous Hall effects as the leading order without any lower order Hall effect present. And of course, also to do this at room temperature and thin films with a hope to perhaps in the future make this as a useful quantum effect. With this, I'm at the end of my first part. If there are no questions of urgent kind, I would just continue to the second part.
Well, I don't have an urgent question, but maybe anyway, I could ask. I was wondering about this. So this is like a relatively thick film, was 30 monolayers or so. So like in the physical picture, is there anything changing if you go to a monolayer, or is it just experimentally more inconvenient? Or?
Let's say we replace inconvenient with challenging.
Yeah, okay. Yeah.
Of course, as a matter of fact, like going to the monolayer is everybody's dream. Being an experimentalist or a transport person. No, the challenge, as a matter of fact, is really to realize a thin film growth. Like iron and tin like to stick together, but they don't like to stick to substrates. So growing these thin films from a sort of kinetic viewpoint of synthesis in MBE synthesis is rather challenging. And for this reason, so far, we were not able to grow true Kagome thin films. Of course, now, if you choose a kind of 2D Kagome toy model, you would, of course, expect these effects to become particularly strong, right? If you really can gap out this sole Dirac cone and you don't have any other dispersive bands present, all these effects would be much stronger.
Yeah, all right, thanks.
Yeah, but I guess the question about the how the Kagome model maps into a realistic scenario will be something I will address now in the second part of my talk. All right, so if there's no other question right now, let me just continue with the second part, where we now try to access the localized electronic states of Kagome flatbands. I mean, as I mentioned already in the introduction to this talk, there has been quite some research activity happening in the past years, mostly looking at the localized electronic states and many body states emerging in Kagome, in Mori superlattices. From a conceptual level, of course, the idea is that if electrons are very localized, basically they have a quenched kinetic energy, interactions between charge carriers can become very strong. And as a result, new many body states can emerge. I think that's the overall picture that we are all very familiar with. Now, obviously, for twisted bilayer graphene, it turns out that this has worked wonderfully well. And soon after, this idea was, came up in maybe around 2010. Pablo Relucero's group at MIT actually managed to showcase the effect of electronic interactions in partially occupied flatbands by detecting superconductivity, mod insulating states, and by now many more states. Now, as I said, Kagome flatbands are actually a very interesting venue to also study these characteristics. We have these destructive interference-derived electronic flat bands, which are supposed to have, relatively uniform distribution across the Brera zone. Now, the question is, where can we find that? And that's actually the challenge. Unlike, say, Mori materials, where by the virtue of just combining two atomically thin material layers, we have a very controlled environment. Turns out it's quite hard to find Kagome materials that have a very well-defined electronic band structure of the type here shown on the left. What you see here is essentially the model calculation of a s-orbital single orbital per lattice site Kagome lattice, right? It has basically 3 bands of flat bands, and here the other 2 bands giving rise to the Dirac cone. In reality, the situation is more challenging. First of all, you have interlayer couplings between the Kagome planes stacked in the out-of-plane direction. Now, obviously, when you say, well, destructive interference helps you to kind of catch an electron and jail it in this honeycomb, the out-of-plane hopping gives it a, an escape pathway, which is something you don't want. Also, just including spin-orbit coupling, which in most materials of interest is hard to avoid, the flatband gains a finite dispersion. So naturally, the question arises, where can we find, which materials can we find true 2D Kagome flat bands, and how can we make them useful, so to say? Now, in the past years, some advances were made, and in particular, cobalt tin was identified as a relatively promising material candidate. As I mentioned before, these iron tin family with a 1:1 stoichiometric ratio has the benefit that the Kagome layers here are essentially stacked on top of each other in basically AA stacking, but separated by a stannine layer in between. And this is advantageous because it now basically suppresses or reduces the influence of these out-of-plane hoppings that essentially would allow electrons to flee the jail. Moreover, cobalt tin turns out to be a paramagnet, and it doesn't have any long-range magnetic order. Of course, this can be challenging to analyze theoretically, but the clear benefit is that the flatband is not subjected to any sort of magnetic exchange terms that are known to destroy, for example, the flatband of iron tin or even iron 3 tin too. Now, it didn't take long until people also could detect this flatband here using ARPAS measurement, where it essentially appears as a rather narrow band, a little bit below Fermi energy. Now, the natural question arises, if we can essentially detect these flatbands, we know they exist in nature with perhaps some, it seems, finite small dispersion. How localized are the electrons? And another interesting question, which came to our mind as we were conducting these studies, is how can we actually distinguish such a localized Kagome flatband from trivial localized states? Say, when you conduct an ARPAS experiment, you cannot necessarily distinguish between a surface resonance and a Kagome flatband. Both appear dispersionless, but it's actually quite challenging to make a distinction. It turns out SDM measurements are quite suited to make this distinction, as you will see in the following. So we have perhaps some large percentage of SDM audience. I'm not sure about that. So let me just give you a brief rundown about this measurement technique. So what we're essentially doing here is to use a sharp metallic tip and scan it across a sample surface. And if we do this under reasonably well experimental conditions, we can visualize the atomic lattice structure. I think what is more interesting nowadays for many of us experimentalists is the ability to study the local density of states of a material atomically resolved. How this works is that we essentially apply a small bias voltage modulation between the tip and sample, and then basically study the differential tunnel conductance. And it turns out that this DIDV signal is directly proportional to the local density of states as a function of energy, which just maps directly to the applied voltage. Neatly, when we fix our applied voltage to a specific value, for example, here to this peak, we can then map out the spatial distribution of this DIDV amplitude. So what you see here, for example, is the topological edge state of bismuth 111. Here in Hong Kong, what we have been doing, I was already introducing before, is setting up this MBE SDM facility that allows us to grow these thin films in this MBE, and then directly using this transfer arm, shove them into the SDM here. The advantage of this approach is that we can grow a sample and essentially study its surface within an hour after deposition. And this is actually quite nice because it facilitates a very fast turnaround time, which, as many of you may know, is quite essential to make efficient progress. From the specs, it's essentially kind of situated at, as I believe, at a sweet spot. It can operate just below 1 Kelvin using a Joule-Thomson cycle, and also allows us to apply I would call it sizable magnetic field for studying, vortex lattices, spin polarized measurements, and so on. Yeah, so this has been set up by my group about a year ago, and now you can see the results of our most recent work. For cobalt tin, it turns out MBE growth is quite challenging. This is mostly related to the chemistry of cobalt, which is a little bit more challenging than that of iron. So what we have been doing here is to grow a nominal film of 50 nanometers on top of, in this case, niobium-doped STO111. While the read observation during growth looks somewhat nice, this can be quite misleading because when you, for example, take AFM topographies of such a film, you'll find it's kind of a patchy film with a lot of islands. As a matter of fact, because of the growth kinetics and the relatively weak adhesion of the cobalt atoms and the tin atoms to the substrate, we find that this film now grows in a Fulmer-Weber growth mode, where you can still realize 100 nanometer wide islands, but not yet, at least, a continuous film. It's also worth noting that there are many other phases existing in the phase diagram. So while we can detect a relatively strong cobalt tin phase in some samples, like here, we can also detect other phases that may be a little bit of a nuisance. In any case, for conducting SDM measurements, as we know, we don't need much. We just need maybe 50 by 50 nanometers, or sometimes even less. So for this purpose, these films are suitable. Yeah, and when we now do SDM measurements on these types of samples, of which you just have seen the AFM topography, this is what we get. So we can, using this MBE growth, still realize fairly large islands with very flat surfaces, which are also, and this is important, atomically clean. When we zoom in, we can resolve this kind of honeycomb looking like structure, which corresponds to the cobalt-free tin surface termination. Why it looks like a honeycomb, I will tell you in a moment. When we do now spectroscopy on the surface, we detect a relatively sharp peak structure just below Fermi level. And now, for those who perhaps have been studying twisted bilayer graphene and other materials that have a flat band, we all know that this is kind of the telltale sign that it's sort of like the minimum requirement to, I guess, study flat band physics, right? I think this is even much broader than perhaps what most people see, or what even myself I've seen in twisted bilayer graphene. Of course, we're not the first ones to do that, and also people before studied this compound here using DFT calculations. Essentially, what you find is that the multi-orbital nature of your cobalt atom having dx, y, dx squared minus y squared, dxc, dy is the orbitals, and so on, gives rise to a relatively large set of bands. The important part is now when you focus just below Fermi energy, where you can find this Kagome flat band. Well, it turns out it's not completely flat. In this case, because of the out-of-plane interactions and spin-orbit coupling. However, we'll show in the following that the electrons are quite localized regardless. So what I show you here now is essentially what has been done before. What I will show you in the following is what is new when we try to directly visualize this non-trivially localized electronic state of a Kagome flat band. The way we do this is to use spectroscopic mapping. More specifically, what we're doing here is now to zoom into this picture I've shown you before, and then record the DIDV amplitude at different bias set points. For example, when we set our bias voltage to somewhere below the flat band, and it's the same if we set it somewhere above the flat band, we essentially record the following characteristics. Here, the DIDV amplitude essentially looks or reproduces in a way the topography of our cobalt-3 tin surface. Interestingly, when we now set the bias voltage to somewhere inside the flat band and then conduct these measurements, we see a contrast reversal. Instead of picking up a strong amplitude on the Kagome ring, like it was the case outside of the flat band energy, now we detect an enhanced amplitude inside the Kagome lattice honeycomb, okay? And this is quite an interesting observation. To understand this phenomenology, we have been setting up a basic tight binding model, which is spinless, but comprises all the d orbitals per lattice site, where the atoms are now shown here as white dots. Interestingly, when you look at the dispersive band, so I think this is now the dxy, dxc band, we find that the local density of states, in a way, is located between the atoms on the lattice structure rim, and in a way reproduces this honeycomb pattern that we both detect in the mapping experiments, but also the topography. In other words, what we're basically doing here is when we map outside of the flatband is to visualize the dispersive electronic states whose spectral weight resides at the atomic lattice positions of the cobalt atoms. By contrast, when we go inside the flatband, even here, the tight binding calculation can accurately reproduce what we have observed in our experiments. Interestingly here, as we saw in our measurements, the density of states of flatband 1 and 2, in this case, I believe this is a dxy, dxc, dyz, and the lower one should be the dx square minus y square flatband. In both cases, the spectral weight is localized in the honeycomb center of the Kagome lattice. So what we detect here is fully consistent with our experiments. More broadly, and I think why this is such an interesting observation, is that this contrast reversal, what we find, or the strong amplitude of the spectral weight of the Kagome flatband at the lattice center, is a direct consequence of the destructive interference-based localization mechanism here. And by virtue of this contrast reversal, which in fact is quite unique to d-orbital derived flatbands, we can essentially distinguish now this Kagome flatband density of states from other states, such as dispersive states we showed here, but also simply maximally localized orbitals or surface resonances that, in principle, also could show a somewhat localized structure at a surface in SDM measurements. All right. Having done this step, we now ask ourselves, so what is actually the localization length of the electronic states, right? Detecting this kind of localized picture in response is kind of cool, and to be able to really identify the Kagome electronic states is cool. But how localized are they? Are they actually suited to eventually lead to strongly correlated states? And the answer is yes, they are. So surprisingly, when you look at the results from DFT calculations, it's predicted that the localization is on the order of perhaps 7 angstroms away from this Kagome honeycomb center. Now, what we find when we essentially take line cuts along these maps and analyze the amplitude decay of the DIDV signal, we find that the localization length is much shorter. As a matter of fact, the electronic states are localized at length scales of perhaps 2 to 3 angstroms, which you can see is almost half the value of what people predicted from DFT calculation. So I wouldn't necessarily say that DFT calculations are wrong here, but perhaps they're not accurate enough to actually account for all the extra correlation effects that may appear in this d-orbital derived electronic states. Yeah, we also find that, and I think this is a detail, but perhaps worth noting, that when you look at the 2 different flatbands, one residing at slightly higher energy, the other one at slightly lower energy, that they exhibit a little bit different response to the about 2% tensor strain that we find in our cobalt tin thin film. And while this is a little bit of a detail, it sort of illustrates that both these states probably derive from different flat band orbital states. Right. So before I come to the end, of course, we ask ourselves, how can we further characterize the flat band properties? The first thing we said is, look, we can essentially now use surface defects to test for the dimensionality of these states. We all know, or we are aware of this very famous example by Mike Cromie and his co-workers back at IBM, when they used this quantum coral to visualize essentially these standing wave patterns of free electrons. And we kind of took on this idea to now use surface defects on the surface of cobalt tin, in our case step edges, to study the dimensionality. Intuitively, you would expect that a 3D electronic state that extends into the bulk of your sample doesn't really care about the presence of step edges. And this intuition is somewhat consistent, for example, with the electronic states at very low energies, which can be ascribed to the dispersive Kagome bands. Here you can see those states barely care about the presence of the step edge, which is basically in this region and this region, when we take a line cut along these 2 step edges. On the other hand, when we now investigate the local density of states of the Kagome flatband and see how it behaves as now the tip approaches such a step edge, we can see that it decays strongly. And this is interestingly, somewhat direct indication that the Kagome flatband states truly have a two-dimensional character. And this is also consistent with results from ARPIS measurements, which found that these flatband states show very little dispersion into the out-of-plane direction. Another question we ask ourselves is that how can we further characterize the actual flatness of the band? We knew now that the electrons are very localized at 2 angstroms localization length. But what does it mean in terms of the electronic, like the band properties? To answer this question, let's go back here and look again at one of these step edges. So when we look at, for example, such a spectroscopic line cut measurement, I told you, we find that the flatband density of states decays towards the edge. What we also find, however, is highlighted here, is that around the flatband energy, we detect an edge state. Now, there has been quite some discussion about the topological character of this edge state, which people believe it could be of non-trivial origin. Here we focus now on using this edge state as a probe to determine the quasi-particle velocity of our flatbands. We know from ARPIS measurements that basically at the gamma point, the quadratic band touching is lifted, and there's about an 80 milli-electron volt spin-orbit-used gap between the flatband and the Dirac point. Now, if we take this as at face value and also investigate here the spatial decay using a simple fit function, we can then directly calculate the quasi-particle velocity inside this flatband. Interestingly, we find this to be on the order of a little bit less than 10 to the 4 meter per second, which is a very small value. So how can we put this in context? So when you think about flatband electronic states, I told you what we want are electrons that are very localized, so that the many body interactions, Coulomb interactions between these states can take over. I've shown you now that in cobalt tin, the states are very localized and that the flat band is actually relatively flat with a very small quasi-particle velocity. When we compare this to, for example, magic angles with bilateral graphene, we find that the effective quasi-particle velocity in cobalt tin is actually not that far away from that value. However, what distinguishes now both materials is that, for example, in twisted bilateral graphene, we have a relatively large 1-year state length scale of above 10 nanometer, which then maps to a relatively reduced on-site Coulomb repulsion. And while, of course, the control and realization of these, say, Kagome metals is more challenging, this very strong localization at the atomic scale, also combined with the d-orbital nature, is predicted to result in relatively large on-site Coulomb repulsion terms. In other words, if we are able to now tune this very flat band with very localized charge carriers to the Fermi energy, there is reasonable hope to find strongly correlated states once we're able to partially occupy these flat bands. And as a matter of fact, this is ongoing work, and I can't talk about it now, but you're welcome to visit my APS talk when I will. And otherwise, of course, future work lies also identifying other flatband material platforms of Kagome type or others. Just this week, actually last week, there was a very nice publication by the Characterization lab at MIT where they found true 3D flatbands in pyrochlor, calcium, nickel 2. Yeah, so if you want to learn more about this work, I invite you to visit our preprint here on the archive. And otherwise, I reached the end of my talk, and thank you for your attention. You can see, apart from building a lot of experiments and doing, hopefully, I could convince you interesting physics, we also do all this type of stuff right at the beachfront. So if you want to do really good physics, but also live at the beach, this is the place. And with this, I thank you again, and I'm happy to answer any questions you might have.
Yeah, thanks for the very nice talk. So, questions? Well, while people are getting going, I had, of course, a couple. in your flatbands at step edges, it
Yeah.
looked somehow like it was asymmetric, that the decay length on the high side of the step was different from both sides. So any idea?
let me just go there.
Yeah,
here.
No, the other slide.
Here.
Yeah, here, if I look at the color scale, basically you indicate with the dotted lines where the step is, and then I think on the low side of the step the flat band starts right at the step edge, and on the high side it doesn't. Is this somehow
interesting? Could be a color scale effect. Well, this is a very detailed observation I didn't pay attention to. What I can tell you, however, is that what we see here is relatively robustly appearing across various sample growths and step edges. Let's put it this way. We didn't pick up anything that was sort of out of line with what we found. But what you can see here, and this is something I maybe just briefly want to highlight, is that you can see the step edge. Only one step edge here seems to show this edge state. I didn't talk about that. And as a matter of fact, what turns out is that this edge state essentially can appear on all edges, but it's kind of termination dependent. Okay, so let me see. You can see this here, for example, right? It's kind of here and here, but then you change the termination as it wraps around the corner and it's gone. So that's something to, of course, also keep note of. But yeah, that's relatively consistent across all the preparations we have done. Yeah.
All right, thanks. Maybe I had another one also. So yeah, basically you say that, okay, the localization length is shorter than you would expect based on DFT, and this could be because of correlations or something like that. Is it somehow obvious that correlation should reduce the localization length? Or?
That's a good question. Well, I kind of gave a very sort of a hand-waving answer, but let me be more specific. So I think, first of all, the challenge with DFT is that, especially when it comes to these, de-orbitally derived systems, it's not very accurate, right? Of course, it gives you a qualitative picture about, okay, there will be a flat band and it will derive from these and that orbital. So this is all good. I mean, this is something we can clearly rely on when using DFT. But when it comes to say, a quantitative understanding what's actually happening with the dispersion and the real space distribution of the local density of states, I think it's hard to rely on DFT. It's not accurate enough. Specifically now also for cobalt-tin, we have to keep in mind that cobalt-tin is a paramagnet, right? It's a strong paramagnet. But we all know that DFT of paramagnets is basically like nearly impossible, if not very challenging, yeah. So what most people have done, like to calculate these band structures, and include ourselves here, where is it? Like here, is simply to switch off, the magnetic interaction in DFT, right? So this band structure, which we now take as sort of at face value, right, is not accurate quantitatively, okay? So, and yeah. And then also there are, of course, we believe interaction effects that in these, de-orbitally derived bands should be stronger than perhaps what DFT here inside these limitations can capture.
All right, thanks. I think Jose was first then.
Yeah, thanks a lot for the wonderful talk. So I wanted to ask you about the origin of this width of the flat band. And as you mentioned, there can be, let's say, interlayer hopping that increases the bandwidth. And there could be also, for example, second neighbor hopping within the Kagome lattice that also increases the bandwidth. So is there some signature in the experimental data that one could use to somehow distinguish between these two possible mechanisms?
Wow, that's a theorist question.
Yes. Sorry,
no, this is a very good question. Of course, these are sort of like the signatures one strives to find. But let me say it bluntly, no. The reason is that this is a very complex system, right? I'm showing you these beautiful pictures, which all make sense when we look at this very simple toy model. The details are described now. Actually, I'm not in this preprint. You have to wait for this. But it's basically a simple Kagome type binding model that assumes a spinless system with all the d orbitals per lattice side, and simply then makes STM simulations based on the calculated eigenstates using a realistic atomic nuclear ion radius of cobalt. So there's no magic involved, and you can already reproduce our observations. But of course, when it now comes to making more realistic comparisons, it's very challenging. First of all, where do we start, right? And when you look at, as I told you, DFT can even not reproduce the spectral shape of your flatband local density of states. And I gave you already some reasons why it's not that accurate. This being said, looking at these pictures, really deriving more insights from, say, the spatial decay of these states, I'm sorry, this is probably beyond what we can do for you.
Yeah, thanks a lot.
Great. Fabio?
Yes, I have a little bit of a mean question, because you were making this kind of like strong statement about the decay of the flatband. Maybe you can go back to the data where you compared this to like DFT. You made this fit.
Here.
No, I think it was still previous. Where we had two graphs where we were fitting like a Gaussian or something.
Oh, here, yes, yes.
So since it's sort of like we're a little bit like saying, okay, here we show that DFT is wrong roughly. Let me play the devil's advocate and ask you, do you really think this is an accurate enough way to experimentally determine the decay length to make such qualitative statements, especially since you're probably doing this in constant current, I guess?
Spectroscopic mapping, actually, multipass. No, we basically, well, so let me give you two answers. So at a technical level, it's a very good question, because this is something we really bogged our heads on for long, because, you know, how can we identify these states to come from a flat band? And I hope I could show you convincingly also by using these toy models that this is something very unique, the spatial distribution. Now, at a technical level, how we measure this is we use what we call multipass. We basically take a constant height, take constant current measurement and record the C topography, okay? And we do this outside of the flat band near the dispersive states to essentially visualize the topography. Once we have that, then we basically go back and then play the C profile while we record the DIDV amplitude at a given set point, okay? So it's not exactly a constant height measurement. It's sort of like a corrugated constant height, well, a corrugated topography that we follow while we map out the DIDV amplitude. And with this, we hope to be the least sensitive to any set point effects. Now, if this is the right way to determine the localization length, how to tell? I mean, it's obvious that what we do here is we basically overestimate it, right? You can imagine that here you can see now the red line already goes up here. If I would put now a second Gaussian here, right, to pick up the next spectral wave, it would already contribute to this one here. In other words, the real localization length would even be a little bit shorter. To say if DFT is right or wrong, I haven't said that. I think it's just not accurate enough to make predictions on this at a quantitative level. And I think this is really the value of experiments here, that we can go down and check this ourselves, since the values. But also, as an answer to Jose's question just before yours, moving beyond that to really understanding why that is. Of course, one can set up other toy models, perhaps more complicated ones than the ones we used here. But of course, this is very challenging to really understand the origin of what we find.
But if you're thinking that your tunneling current or your DIDV is sort of like getting the square of the wave function, if you would take the decay constant of the actual wave function, you would have to half this, right? So maybe that's the factor of 2 you're missing. I don't know. I mean, just find
you can just, yeah, I mean, but eventually you can calculate the LDOS also from your measurements, right? From your from calculations, and just compare it. And so yeah, that's what you get. Yeah.
Okay, thank you.
But you're right. I mean, the limitations in the approach we take. Yeah.
Okay, thank you.
Okay. We have a question in the chat from Shomes. So, do you see any change of the conductance maps as a function of the applied magnetic field, similar to the iron tin system?
I believe the question addresses cobalt tin.
That's indeed. So, similarly to iron tin, do you see anything in cobalt tin? At least that's how I understand.
No, we have not looked at that, to be very honest with you. Because the flatband resides below Fermi energy, we didn't expect any necessarily interesting things to happen. But certainly right now, we take measurements with magnetic fields, and please bear with me. But the results I present here are basically, they should not depend on magnetic field.
All right. I think with that, there seems to be no more questions. So let's thank Berthold once more. Thanks a lot for the nice colloquium.
Yeah, thanks for being here and listening, everyone.